This is for linear model. So this one a linear model. So you just give a linear model, meaning that all are using original values of variable y and x. So yes, it's the model. So this one left question 2, question 1. So how does it model? Just like before, you go to so if you don't know how to prepare data to this one way, you learn how to prepare data. I mean, you have data in the word file. In the word file, so you want to prepare data. So I think I give many of you already know how. But you don't know, you can see. So I show you how to prepare this data. So quick estimate equation. This one at section 2Q1. Okay, so you have your dependent variable. So I mentioned before, you can just use this one. You can put y space y equals c bracket 1 for intercept plus c bracket 2 star x1 plus c3 c bracket 3 star x2 also can, but this much easier. So you just put dependent variable space c for intercept space the list of your dependent variables. So you have x1 and x2. So okay, so you get an estimate. So c, the estimated value of beta 0. So this one, the estimated value for beta 1. This one, 0.51. Estimated value for beta 2. So we need option for x2. So the next question, test the null hypothesis that beta 1 equal to 7.5. So you notice that here we have, so beta 1, this one not beta 1, then this one is the estimate of beta 1. But the question asks you to perform a testing that beta 1 equal to 7.5. So we need to perform this test. Okay, so recall that you have t statistic and p value here as well, but this one can only be used, this one, the one that given in computer output, can only be used if you test beta 1 equal to 0 against not equal to 0. If your null hypothesis, this one equal to 0, alternative not equal to 0, then you can just use this t statistic. Because this statistic is calculated by taking this divided by this divided by this. Okay, so if the question asks you to perform the significance of beta 1, then you can just use this one, or you can just p value 0.01. If you perform the test at 5% significant level, then you say it's significant. Significant because it's less than 0.05. But the problem now, question asks us to do this hypothesis. Not 0, but 7.5. So you cannot use this one because the t statistic is not calculated. It's not calculated for this one. Because remember the formula, the estimated value minus the hypothesized value divided by SE. So the one that given in computer just now, it does not minus this one. It just divide this divided by this beta 1 hat estimate divided by standard error. So it's only for the case of 0 because minus 0 lah. Okay. But now we want to test whether it is equal. Let's say someone asks you to test whether can we just assume that, or can we just conclude that the effects of x on y, when x increase 1, then y will increase by 7.5. Okay, so we need to perform this hypothesis. So in order to make conclusion, you have to calculate, because you cannot use the one that given here. You can use this one, beta 1 hat, you can use SE. SE is one, SE. But you cannot use this one, you cannot use this statistic because this statistic is calculated. This minus 0 divided by this. This minus 0 divided by this. But we want this minus 7.5 divided by this. Okay. So you have to calculate your own t statistic. You cannot just use this statistic, you cannot use the t value because this one is not minus 7.5, it's minus 0 divided by SE. So you just take the estimated value 7.5, 7.4 minus 7.5 divided by SE, this one. And you get negative 0.01366. You don't have the value, like this one. Okay, so you calculate, you have to compare to critical value from T table. So how to identify the critical value? So this is two-tailed test. So you have two sides of rejection region, the positive side as well as the negative side. So you perform the test at 5% significant level. When you refer to the table, refer to 5% divided by 2. 2.5%. Huh? Do I need to show how to find this critical value? Do you want me to show how? Last time I already showed, right? So how to find for two-tailed test? Because this question does not mention at what percent. Normally we just use 5% significant level lah. Okay, but if the question asks you to use 10%, then use 10%. It depends lah. Okay. If the question does not mention, you just use 5%. Normally we use 5%. So we refer to T table, critical value, sample size we have how many? 20. So T minus K minus 1. So K is number of X. So 20 minus 2 minus 1 for intercept. So that's why we have this one. T minus, oh we don't have it here, I mean that's not mentioned here. Specifically we have 70 is, sorry not T, N minus K minus 1. Degree of freedom, N minus K minus 1. So K is number of X. So we have 2X. And then minus 1 for the intercept. So intercept also need to be estimated. So sample size minus 3 parameters to be estimated. So minus 2 minus 1, so minus 3. 20 minus 3 is 17. Okay. 17 you refer to table, T table. The one in which folder I provide? Page 1, 2, T table. So okay, please make sure you know how to find this one. So if you perform the test at 5% significant level, 0.5 because this is two-tailed. Why two-tailed? Because alternative not equal. I mentioned before is alternative greater or less, that one is one-tailed. So not equal to tail, two-tailed. So you have two sides of rejection region, positive side, negative side as well. So your alpha you divide by 2 because two sides. 0.05 divide by 2, 0.025. So refer to table 0.025, degree of freedom 20 minus 3 which is 17. Sana. Okay, 0.025 and minus 20 minus 3 is 17, so 2.11. So your critical value 2. Both sides, so you have positive 2.1 and negative 2.1, both sides. Okay. The positive side as well as the negative side. And then your T statistic negative 0.013, there is in between the two critical value, positive and negative side. So you do not reject. So conclude that we can, it is safe for us to say that the true value of beta 1 is equal to 7.5. So we can accept, like we say, we can agree that beta 1 is the true value. Now estimate is beta 1 hat. So estimate just from one sample, remember? The difference between sample and parameter. Parameter is for population, there's only one value for population, but we don't know. So by using this approach, then we can say that, okay, I can agree that the true value of beta 1 is 7.5 because we did not reject lah. Okay. So this is actually in between. So within the exception, we did not reject within the exception. Okay. Method 2 and method 1 lah. Method 2, you can use walk test, also discussed in the recorded explanation. So in order to use walk test, you can use this formula. But in order to use this formula, you have to get as some square of error for the full model and a restricted model. So full model is original model. Okay, and restricted model is the model when if the null hypothesis is true. So the null hypothesis says that beta 1 equal to 7.5. So you can replace beta 1 with 7.5 here, and then you rearrange the equation. So you can bring, because here we already put numbers, so we don't need to estimate. So you can bring this to this side, so it becomes a new dependent variable. So y minus 7.5 x1, and then you only have x2 as your replacer. Okay. So you estimate this model, you get SSE, and then you can calculate, you get this one, and then you compare with the theory from F table. So this is F table. Okay, so for the model that we estimate just now, you use then you can perform walk test easily without having to estimate the two models separately. You can just estimate the full model. Okay, you just, for example, I mentioned before during the midterm test. For the midterm, for example, you have two options whether you can just perform the walk test by choosing this one, or you estimate the full model and the model. So don't waste time. So during the test, use the easier one. Okay. So the final exam, you need to know both. You may say you are only, let's say for example, final exam, you are only given information about SSE for the full model, SSE for the restricted model. Then you have to use this one. You have to calculate this, and then you compare the value from table and then make conclusion. But if you have in use, you just need to estimate full model, this one. And then, so this is coefficient number 1 for intercept, coefficient number 2 for beta 1, coefficient number 3 for beta 2. Okay, coefficient number 1, number 2, number 3. So your beta 1 is coefficient number 2. Okay, coefficient number 2 equal to 7.5. So you go to view, coefficient diagnostic, walk test, coefficient number 2 equal 7.5. Okay, so you just press OK, and you get the T statistic. That's the one that we get just now, or the F test. By the walk test only we use the F now. So F test statistic, you use then you get p value. So p value much greater than 0.05. So you do not reject. Remember p value, how to make conclusion based on p value? If greater than alpha, we do not reject. Smaller than alpha, we reject the null hypothesis. So F test says the p value greater than 0.05, so we will not reject. So again, we conclude that we can agree that the true value of beta 1 is equal to 7.5. So this is the full model. So this is the one that we estimate now, is the full model. I just want to show you, let's say you want to estimate a restricted model. So this is the full model, equation 1, full model. So you want to estimate a restricted model, this one, restricted model. So you have y minus 7.5x1 and then x2. So you have y minus 7.5 x1 and then you have intercept, you have x2. If let's say you want to calculate manually, okay. But you have to use no need to do this because you can just easily perform the mock test. Just like what we did just now. Just in case for an exam you are given the output of full test and then the result the output of full model and then this is the model which is this one. So y minus 5.5 x1 c x2. Okay. So you get this one. But this one because it's very large value, so this one SSER. This one SSEF. So this one is used because it's very large value, so it provides scientific number. But if you use Excel, then you are able to get exact value. Just like the one I given here. This is actually can be obtained from Excel. You use Excel, then you get this SSE. But if you use because it's large value, too large value, so if you use this value, then we just the same. This one divided by this one. I mean, so not that accurate. But again, if you have to use them, you can just perform the test by going to this one, completion the work test. Much easier. Okay, but you still need to know how it's calculated. So, do not only know how to use software, make sure you know how it is calculated. Otherwise, everybody can learn how to use, to use the software. Alright, so this is our restricted model for question number for B, 1B. Now 1C, test another test, perform the analysis that beta 1 equal to 15 times beta 2. Okay, so coefficient number 2 equals 15 of coefficient number 3. Okay. In your model just now, because C, the first coefficient for intercept C. Okay, so this for beta 1, this one for beta 2. So we want to test the null hypothesis that beta 1 equal to 15 times beta 2. So coefficient number 2 equal 15 times of coefficient number 3. Okay, so just like before, you go to view, coefficient diagnostic. You perform the test on the full model, no restricted, full model. Full model, so view, work test, coefficient number 2. You have to be careful. I think there is some incident before some student. Just few student. They put C bracket 1 equal to C bracket 2, then correct. It produce incorrect test p value. So 15 times of, it depends on how it appears here. It depends how you, the order lah. If let's say you put C at the last one, then then you have to follow that one lah. So let's say you put, when you estimate, you put Y space X1, X2, C. C you put the last one, then your intercept is the last coefficient. Okay, but this one according to how it appears here. So C2 times 15 C3, you put star C3. So okay, so you get your F statistic 0.004, P value 0.94, then you can, this one reject as well. Oh sorry, this one do not reject. Do not reject. So if you calculate manually, then you have to estimate full model. Full model is like before, and if the null hypothesis is true, what happens to the model? So you can replace not beta 1, you replace this. Beta 2, you can replace this beta 1. Because beta 1 equal to this one, so beta 2 equal to beta 1 over 15. So you can replace beta 2, becomes beta 1 over 15, and you rearrange. Now you get a new model. So you estimate this model, then you get the SSER. Okay. You understand this one? I don't need to show, right? Just like before. So if you do this, then you have to compare basically from F table. F table, you have 2 degree of freedom. So the degree of freedom is always from here, the formula. So G and this one, G and N minus K minus 1. Because F has 2 degree of freedom. G and N minus K minus 1. So 1 and 17. So you refer to F table, 1, 17, the column 1, row 17. And then you choose the first row within that one, 45%. Silicon level, so you get your critical value, 4.45. So your F smaller than critical value, so do not reject. So it is within the exception, not rejection, exception region. Okay, so question number 2. So I close this one. Close this one. So the following table. So we have number 2. We have 5 x 1 dependent variable y. So we have, so estimate is model, so similar like before. So you have this one, that's section 2. Open the second one. Okay, estimate model, same, go to quick estimate equation, and then just put y space c space x1, x2, x3, x4, x5. So y, this one based on what you put the name, not based on the name variable. If you name the variable using GDP or whatever, do not put y, put that the name of variable. Just like what we did before, average cost and the cost. Don't put, when you estimate model, don't put y and x. You cannot find y, your y is your y. What's your y, what's your x? So this one y space c space x1, x2, x3, x4, x5. So okay, so you have your slope, also you have intercept, and then beta 1. This one estimate, estimate of beta 1, or we call it beta 1 hat. This one beta 2 hat, beta 3 hat, beta 4 hat, beta 5 hat. And then test this hypothesis. So we have two restrictions. Okay, so I mentioned before the formula G is restriction. How to know how many G equal to what? So G equal to how many restrictions we have. So previously question number 1, we only have one restriction. So this one is only one equal sign. So you just count how many equal signs you have. So this one we restrict beta 1 to be this one, so one restriction. This one also the same. We restrict beta 1 to be 15 times beta 2, so there's one restriction, one equal sign. But this one, you have two equal signs. So beta 4 equal to 0 and beta 3 equal to beta 5. So two equal signs. So if you need to calculate manually, your G is 2, not 1. Okay? Your G here, G. Number of restriction. Number of how many equal signs you have? How many restrictions you have here? 1, 2. Okay? Previously question 1, you have 1. So you can do the same by estimating full model, Rodian model, and what happened to the model if the null is true, beta 4 equal to 0, then you put this one 0, beta 3 equal to beta 5, so that beta 5 you can replace beta 3. So beta 5 you can replace beta 3 and then you arrange you get the new equation, so this is your restricted model. So if you have to calculate manually, you have to estimate full model, get SSE, and then the full model, restricted model, SSE, and then you can calculate lah. So G2, G equal to 2 restriction. And minus K, minus 1 just like before lah. Sample size minus how many X we have, minus 1 for the intercept. So this one, if used, you can easily perform the test. You go to view, coefficient dynastic, work test just like before. So this one you have to perform the test on the full model, not the restricted model, full model. So meaning that you have it used, you just need to estimate the full model only, and then you can perform the test using this option. Here. So beta 4 equal to 4 equal to 0. So coefficient number 5 equal 0. That's the first restriction. Second restriction, beta 3 equal to beta 5. So coefficient number 4 equal coefficient number 6. Okay, so you put comma in between. So I leave it to you to estimate the restricted model at the home. So later at the home, try to estimate the model and calculate manually. So again, final exam is possible that you are given outputs or the full model and this is the model, and you are asked to perform the test, and then you have to calculate. Okay. So that's one of possible question. But make the class test, don't waste time, don't do that. You just use this one. Okay, but you have to be careful lah. You have to type the correct one. Don't, for question number 4, don't put C4. It is because the first one is for set. Question number 1 is set. So question number B beta 4 is question number 5. 1, 2, 3, 4, 5. Okay. So then beta 3, beta 5. Okay. So you get this one. So this one, for more than one restriction, you don't have T statistic, you only have F. Because T cannot be calculated for more than one restriction. So this one, F statistic 0.02, P value 0.97, just like before. This one also greater than 0.05, so we do not reject. So do not reject. Conclude that, we can agree, do not reject. Okay, we can agree that the true value of beta 4 equal to 0 and beta 3 is just equal to beta 5. So later try to do this one, estimate here, this is the model, and then you try to calculate. Question number 2C. So given this formula equal to this one, so meaning that instead of using sum square of error, we also can calculate the test statistic, F statistic using coefficient of determination R square. Coefficient of determination R square. And perform this test. So this is the overall significant, meaning that you perform the test for all slope parameters jointly. So beta 1, beta 2, beta 3, beta 4, beta 5 all equal to 0. So this one, in use, you can get that for if you want to test the slope coefficient for all slope coefficient model, then you can just take this one p value and then f statistic and p value given here. Okay, so this one the f statistic for the overall significant test. So p value smaller than 0.05, so you reject lah. Okay, you reject. You want to use walk test also can lah. You go to this one, walk test, and then you type lah. Coefficient number 2 equal coefficient number 3, 4, 5, 6 all equal to 0. Then you get the same lah. Okay, you get the same. But don't need lah. What you need to do? Don't need to do this because you can get this value here. Okay. Okay, so now it says that here, if let's say, in final exam, for example, in final exam, if you are given this output, this is full model, but you are not given output for restricted model. So in this case, the restricted model is, if none is true, then what happens to the model? So all slope equal to 0, 0, 0, 0, 0, then you only have intercept model. So this is your restricted model that only consists of an intercept. Okay, so let's say, for example, in the exam question, it provides output for this one, but you don't have output for this one. So the question asks, and you don't have this one. For example, you don't have this one. Okay, so you can use alternative way to calculate F statistic using this formula using the R square. So R square you have, let's say R square are given, R square 0.82, 82275. For the case of restricted model, if you only have C, if you only have intercept model, then R square equal to 0. Okay, if they say restricted model is if all equal to 0, then you only have C, you only have intercept. Right, as given here. If they say the null is true, all equal to 0, then you only have an intercept because all is 0. So if you only have intercept, then your R square equal to 0. Because remember, the R square represent what? R square represent how many percent of variation in Y in independent variable can be explained by your X. If you don't have X to explain Y, then the model cannot explain the variation. So it's just 0. If they say if you estimate this one, so let's say you take out all X, you just put intercept, and your R square just 0. Okay. So even though they say you don't have the output for this one, but you know it must be 0, the R square. Okay, without any X, then it must be the R square must be 0. Then you can calculate using the given formula. Then you will get the same. And then you compare to critical value from F table. So this test statistic greater than critical value. So we check. So conclude that at least one of these not equal to 0. So do not say all not equal to 0, but at least one. You do not know this one, we do not know which one. Because this is joint statistic. So we can only, if we reject, we can only say that at least one of them not equal to 0, but we do not know which one. Okay, in order to know which one, you have to perform the individual test. Test one by one, beta 1 equal to 0, and then beta 2 using T statistic. Beta 1 equal to 0, beta 2 equal to 0, and then beta 3 equal to 0. Okay, last one. This is stability test, the Chow test. So we have two variables, unemployment rate and job creation, V. So if let's say we want to know whether for this for the whole period from 1930 to 1980, we can just use the same value of parameter to represent a relationship between y and x, between dependent and independent. So now we want to test whether it is safe for us to just assume the effects of y or v on ut is the same from the beginning of the data to the end of the data for the whole period. Stable or not, the parameter is stable or not. So you need to test, huh? Okay, so if let's say we choose 1962 as a breakpoint, okay, this one, and then you can perform the test. So this one, you open the data. This one, the one. So UN, unemployment is our dependent variable. So estimate model, quick estimate equation. So you have UN space C space V. So you have this estimate. So now we want to know whether these parameter for both in the set n, beta 0 and beta 1, either both of them or one of them not stable, meaning that the value still the same for the two periods, before 1962 and after or starting from 1962. So to perform the test, if you use, then you can just go to View, Stability Diagnostic, the Chow breakpoint test. Okay. So here you need to put the first date of the second period, second part. So they say in this case now we have data and you want to test whether the parameter for the first set of data is still the same for the second part of data. So meaning that before 1962 and starting from 62 and onwards. So in this case you need to put here, you need to put the date or the year. This one because you have monthly data, so you have annual data, you have monthly, then you have to put which one. The first in the second part, the second subsample. Okay, so this one the first one, and the second one is 1962. Okay. So you put 1962. So let's say you believe something happened starting from 1982 that may change the form of relationship between unemployment and job creation. And then you can test that. So you can use 1962 as the breakpoint date. So okay. So then you get this one. The F statistic 88.95, p value 0. So 0 less than 5%, 0.05, so you reject. So you reject, conclude that the parameters either intercept or slope or both of them it's not stable, meaning that we cannot say they are the same before and after 1962. So it is not safe, it is more safer that you split data into two and estimate separately. Okay. If they say, for example, something happened in 1962 that you believe, just like COVID-19 So let's say 2020, we have COVID-19. So we believe that the present of COVID-19 has changed the relationship between variable, and then you can use 2020 COVID-19 2020 as a breakpoint, for example, okay, to test whether it is safe to treat the parameter to be the same before and after. Okay. So this is usually easy lah, but if you want to calculate, to do it manually, what you need to do, you need to estimate the model using all data, and then you split data into two, you estimate separately, subsample 1, subsample 2, and then you get SSE, and then you can calculate the test SSE using this formula. So this is the pool model, the pool data. Just now you get SSE here, sum square residual 4.06. So SSE, this is the model using the pool data, and then after that you split, you estimate separately lah. So you estimate 1930 to 1961, and then you do 1962 to 1980. You understand lah? Understand lah? So this is the pool data. So you get SSE, right? If you want to calculate manually like this using the formula, you have to know this one lah. This is SSE using all data, entire data set. This one SSE1 using the first subsample. This one using the second subsample. So meaning that you have to, just now we already have this one. Now to get SSE1, we just put 1930 to 1961. Okay. If you want to get that value lah to calculate manually, but as I mentioned before, you have it used, then just do it easy way lah, just like we did just now. Okay, so you get SSE for the SSE1, this one, and how about SSE2 is 1962 to 1980. So you get SSE2, okay, and then you can calculate. Using the formula. K number of x you have. So 1 plus 1. And this one. Sample size, subsample 1, sample size subsample 2. And then but this one you have to compare with the value from the table. Okay. Critical value is one. Critical value you do not need to memorize. So you can just look at the formula, and then this is the first one, this one is second, if you have it. Okay, the first if you have it, second. So it is 2 and 47. So therefore we reject analysis. So both model for this example are different. There is partial change between the given time, before 1962 and after, starting from 1962. So we cannot assume the form of relationship to remain the same before and after. So it is safer for you to not to estimate using all data, or you estimate using the one you will discuss later. Then after TP, you can estimate using all data, but you have to introduce some kind of dummy variable to represent the structure change. But the one we will discuss later when we discuss the dummy variable topic. Okay. Either you just estimate separately, subsample 1, subsample 2, or if you want to estimate using all data, but you have to do something to the model by adding dummy variable, for example, to represent the change in the parameter. The one we discuss later. So I think I cannot explain everything now. So later I explain. We discuss the one and then you should be able to understand. Okay, so I think that's all for today. So next week we discuss multi-collinearity.